Welcome to part 5 of my video playlist about the best methods to alkylate amines. This presentation is about some alternative strategies that can be used to alkylate amines. There are many instances where the direct alkylation of an amine with any of the electrophiles discussed in the other videos cannot be used to prepare a target amine. Particularly difficult is, for instance, the monoalkylation of primary amines or ammonia with small electrophiles, or the alkylation of sterically demanding secondary amines. In such cases, a less direct strategy may be superior to the direct alkylation. In this video, I'll also show you some further electrophiles that can be used to alkylate amines. The most relevant are carboxylic acid derivatives and alkynes in combination with reducing agents. Then, of course, many other electrophiles will alkylate amines, for instance oxonium salts, carbenes, epoxides or ethers. Alternatively, amines can also be prepared by reducing amides, for instance with boranes, lithium aluminum hydride or by catalytic hydrogenation. Sterically crowded amides may, however, undergo carbon-nitrogen bond cleavage during attempted reductions. One useful strategy for the preparation of secondary from primary amines is the conversion of the latter into a more acidic derivative, for example a sulfonamide, a trifluoroacetamide or a carbamate. These are no longer as nucleophilic as amines, but can be converted into stronger nucleophiles by deprotonation. Alkylation and hydrolysis provides the secondary amine. Sulfonamides are easy to prepare and are alkylated cleanly at nitrogen, but can be difficult to hydrolyze. Today, nitrobenzene sulfonamides are usually used for the preparation of secondary amines and can be cleaved by thiols. Normal amides are difficult to alkylate at nitrogen. Deprotonated amides are strongly basic and tend to cause beta elimination of halides or other leaving groups. Then, being ambident nucleophiles, amides are often alkylated at oxygen or give mixtures of nitrogen and oxygen alkylated products. Most amides are also difficult to hydrolyze. One exception are trifluoroacetamides, which are readily cleaved by nucleophiles but are stable under acidic conditions. Also carbamates can be alkylated at nitrogen, and benzyl carbamates can be readily cleaved by hydrogenation. Ureas are not well suited for this strategy because these are often difficult to alkylate and to hydrolyze. One strategy suitable for the preparation of sterically crowded amines is conversion into an intermediate chloramine followed by chloride displacement with a strong carbon nucleophile, for instance a Grignard reagent. Chloramines are not very stable and readily eliminate chloride to yield an imine if the amine has alpha hydrogen atoms. Despite this potential side reaction, a number of successful examples of this strategy have been reported. Then, any compound that can be converted into an aldehyde or an imine can in principle be used to alkylate amines. Tertiary amines can, for example, be used as aldehyde precursors for the alkylation of other amines. Such a strategy will be particularly valuable for the generation of unstable or otherwise unwieldy aldehydes. This is an example of twofold alkylation at nitrogen of an aniline with chloroacetic acid for the preparation of the cytotoxic anti-cancer agent melflufen. A large excess of chloroacetic acid and borane were required to attain a complete conversion of the starting aniline. But because of the high price of the starting aniline, this didn't seem to affect the overall costs of the synthesis too much. Interestingly, despite the large excess of borane, no reductive dechlorination or reduction of the ethyl ester in the product occurred. Instead of carboxylic acids, also nitriles can be used to alkylate amines in the presence of some reducing agent. In this example, the alkylation proceeded in the presence of hydrogen and rhodium or palladium or charcoal at atmospheric pressure and ambient temperature. This is surprising because nitrile hydrogenations usually require higher temperature and pressure. Anyway, high yields of secondary and tertiary amines could be attained by this method. This is an example of the alkylation of a primary amine with a terminal alkyne. The two-step synthesis consisted of a Lewis acid-catalyzed addition of the amine to the alkyne to yield a mixture of enamine and imine, followed by a catalytic hydrogenation. In this example, a nitrobenzene sulfonamide was used as intermediate for the large-scale preparation of pramipexole, a dopamine agonist for the treatment of Parkinson's disease. Sulfonamides are very acidic, and weak bases such as alkali carbonates are sufficient to bring about clean alkylations. In this instance, a large excess of propyl bromide and potassium carbonate were used, but no alkylation of the primary amine or the thiazole occurred. The sulfonamide was cleaved by treatment with a strongly nucleophilic mixture of lithium hydroxide and thioglycolic acid. Cysteine would have been another non-toxic, non-volatile thiol with moderate smell only. As mentioned above, amides other than sulfonamides are difficult to alkylate. Because of the high basicity and low nucleophilicity of deprotonated amides, these tend to cause dehydrohalogenations whenever possible. In this example, octyl chloride, bromide or iodide gave large amounts of octene upon reaction with the sodium salt of deprotonated trifluoroacetamide. Only the octyl iodide and mesylate gave good yields of N-alkylated amide. Trifluoroacetamides can be cleaved by weak nucleophiles, such as amines or with aqueous potassium hydroxide as in this example. Thus, the alkylation of unsubstituted trifluoroacetamide would be an alternative to the Gabriel synthesis, in which phthalimide is alkylated at nitrogen and the primary amine is released by treatment with hydrazine. These procedures are usually better suited for the preparation of primary amines than the direct alkylation of ammonia, which often yields large amounts of secondary amines. This here is an attempt to prepare a sterically crowded bis-terzalkyl isopropylamine. None of the conventional isopropylation techniques worked, and best results were obtained by chlorination of the bis-terzalkylamine followed by nucleophilic displacement of chloride. Although no elimination of hydrogen chloride was possible in this case, the Grignard reagent can also attack the chlorine atom to yield isopropyl chloride and the metallated amine, which would then eliminate chloride from isopropyl chloride. This was probably the main reaction pathway. Nevertheless, 15% of the desired isopropylamine was also obtained. Unfortunately, this compound turned out not to be very stable and decomposed already at room temperature. The reason for this lability is the CN bond, which is about 5% shorter and 10% weaker than a CC single bond. This is also the reason why metallated diisopropylamine is a good base but a poor nucleophile. On this and the next slide there are some further examples, but many more have been reported, in particular of the alkylation of imides and sulfonamides. You can also find this list of references in the description of this video. Hope you found this helpful and stay tuned for the next presentations.